Basically, I was trying to use this lecture to cover my past experience in dealing with temperature-related issue in our geoenergy engineering. So I just a couple of days ago, I generated this picture using our AI technology. I improved thermal and energy in cold region, and again this nice picture. You see that now basically the thermal energy stuff is not only for petroleum stuff, it's for coal regions as well. And that fits perfectly to my background for geothermal energy or sustainable energy in coal regions. Another topic I want to cover today is that we can use AI technology to produce nice pictures, but there are something which beyond the scope which AI can do. So we do need our human mind to create something more innovative. So basically, that's why I come up with this kind of a lecture to draw a summary. Um, I'm gonna go with firstly, I'm gonna have a general introduction about the geomaterial as a porous media, the object we are studying. Then I draw a summary about the governing equations and the constitutive laws for controlling the behavior. Then I'm gonna use the finite element method as a typical numerical tool to solve this problem. Then use my past experience to show the application how those things can be connected. Basically, when we have geomaterial, we um, we are talking about computational geomechanics. Because thermal mechanics is a part of our computational geomechanics. People will ask, the AI technology is so popular now. It's a computer can do everything. There we can just rely on AI technology to give me our results. Do we still need the computational geomechanics? Do we still need to burn our mind to do so many critical thinkings for this topic? So that's the question we can keep in mind. So another thing is, how can we obtain the interest of learning computational geomechanics? Because before joining any research team, you have a fancy dream, but when you come up with computational geomechanics, the PhD become permanent had damage. So it's kind of destroy the interest of going deeper. That's a very common phenomenon all over the world. Even here in Canada, people are try to escape from such kind of course. So I was trying to promote this kind of course. Basically, I was try very hard in the past couple of years at Concordia, try to offer such kind of course to our students at Concordia, at McGill, and also Polytechnic Montreal, try to attract students to go into this area and make use of computational geomechanics more efficiently. So basically, I want to use this lecture to draw something which contains a high dimensional wisdom, try to promote interest of learning computational geomechanics. So basically, to me, the computational geomechanics is like a big tree. The big tree, the first thing what we can see is just I think the first thing which appear in the mind is the colorful leaves. And it's very attractive color, or all leaves, it changes color from season to season. But in order to really grasp the essence of the tree, actually we should hold the trunk instead of the leaves, because the leaves will change color from year to year, from season to season. The essence should be the trunk. So computational geomechanics, for example, previously petroleum is hot, oil sands is hot, we go with that. Carbon dioxide is hot, we go with that. Then shale gas is hot, we go with that. So from season to season, the leaves is always changing. Now hydrogen is hot, we go with hydrogen. So basically, the things we cannot just hold the leaves. We basically should leave the trunk to hold the trunk, try to make sure we grasp the trunk, no matter which season it is, we are still holding the tree. So that's something I want to highlight. So after going with the trunk, so let's look at the example of the trunk. So what is the object we are studying? So when we look at the geomaterial in earth science or engineering domain, so the first thing we come up with the rocks is a typical porous media we come up with. So there, because the rock is treated as even a dual porosity media or triple porosity media, it contains fractures, microstructures, and if it is buried very deep, it's kind of related to the thermal-driven fluid flow fracture and also failure behavior. Is heavily involved in deep geothermal energy and deeper petroleum energy projects. So it's kind of a porous media filled with the multi-phase flow behavior. So we have to try to grasp the physics behind this phenomenon in order to have a safe production. The other things in cold regions, what we come up with is in cold regions, it's not only for the climate change induced infrastructure. We have something when we produce geothermal energy, no matter to produce geothermal energy or to their geothermal storage, we may destroy the original permafrost structure. So that's something we have to prevent. We want to maintain the permafrost instead of destroy the original frozen ground. So their study on porous media or thermopore mechanics gonna be study the low temperature range, the frozen part. So basically, it's kind of a multi-phase flow and phase change behavior from solid to fluid as well. That means from the ice to water. That's something closely related to this process. Having said all those geomaterial, we cannot just handle all the details. So we need something which can govern the behavior. The key thing I want to address is the effective stress law. And with the effective stress law, you have the total stress, and we separate the total stress into effective stress and pore pressure. And the effective stress is something which controls the deformation behavior. And with the concept of effective stress, then you are able to get the study the behavior separately for effective deformation behavior and the pore pressure behavior. So what should be highlighted here, the pore pressure here can be a combination of air, water, ice. So it's not restricted only to water pressure, which we usually have. If it is a petroleum product, maybe the pressure from the over petroleum results can also be involved. So it's actually multiple components. So we should find a way to deal with the pore pressure properly. And also the coefficient, when it is soil, this Biao coefficient, we use 1. But when we have a rigid rock, the Biao coefficient can be much less than 1. If we have a swelling soil, swelling rock, the effort can be more than 1. So basically, there are some tricks inside this behavior. The other key things that when we know the main governing, main behavior, we want to rely on physics to construct a mathematical model. I'm going to use one of the complicated unsaturated porous media governing equations to demonstrate what we usually have. If we have unsaturated soil or rock, we have gas. The gas was inside the gas, dry air or water. We have solid phase, we have liquid phase, we have dissolved air. So basically, it's kind of a multi-phase media. The key thing first is that we want to find the balance. The balance of mechanical equilibrium is to deal with the force. The balance of the water mass balance. So basically, the water mass balance can contain the vapor, can contain the fluid, can contain the ice. So basically, it's gonna be related to pore pressure. So the other thing is the air mass balance, which you can have to study the pore pressure from the gas component as well. Then we come up with the internal energy balance, which is to focus on the heat transfer process, temperature balance. And also you need something to couple them. The deformation, the pore pressure, porosity change, how can we link them? Eventually, it's a fully coupled process. So of course, we need some assumption. For example, if we want to make your problem simple, you can neglect the mechanical induced heat, or there are some other melting behavior. You can make some assumption, but eventually it should be fully coupled. This is the governing equation. This is the trunk of the tree. This is like the big tree. The nonlinear partial differential equation is the key, is the trunk. So we figure out something which is controlling the balance. We also need to figure out something which is controlling the change. So constitutive laws is something to control the change. For example, you have stress, strain, how stress is changing and bring your change in strain. So you need to quantify the change. So for mechanically, you can use the big attraction test. And for example, during my PhD, I use a self-designed CT scanner, or under my supervision of my supervisor. We come up with this kind of complicated setup. Basically, you can do high pressure, high confining pressure, and high temperature test, and use high technique to quantify such change, and how the stress strain is changing. And also for hydraulic, you can propose complicated flow model to quantify how the pore pressure is evolving. And the same thing for thermal, how the temperature is evolving in their structure. So the constitutive laws is controlling how the variable is changing. So with something which is controlling the balance, and with something which is controlling the change, so then you're gonna construct a very complicated governing equations and constitutive laws, and that's the mathematical problem now. So we have to rely on numerical methods to solve this complicated mathematical problem. And I want to use finite element method as an example. Of course, it's not the only method, but this is something I use for many years. And also I think it is promising and which is capable to solving this kind of problem. So as an example, a typical numerical method, why FEM is quite strong in solving this kind of problem, I'm gonna use a couple slides to cover. Taking their heat conduction, their problem, which is a typical partial differential equation, and heat conduction if it is isotropic and homogeneous, and it's just the second degree of partial derivative, and you have an influence on domain omega, and you have the boundary condition first and the second type of boundary condition. And before we move to any finite element group of numerical tool, you have to derive a very important procedures to convert your strong form to be the weak form. And why we want to do that? Because the strong form is very difficult to solve. You have analytical solution, but it's very restricted to very specific boundary condition or assumption. You have to convert to be the weak form. The weak form was derived based on apply a small disturbance and convert your governing equation to be an identity with the solid physical meaning. For example, as a scalar, as a value, you can convert to be, for example, energy or whatever. Eventually, you will find it's in an integral format. And for the smallest, with the small disturbance, actually with the variation, your partial differential equation come out with the first order differential equation and just multiply by twice. With this, with this kind of a small disturbance, the derivative is reduced by one order. That's why the FEM group of numerical methods is kind of very accurate. And this kind of weak form is the start of a group of advanced numerical methods. Lately, you have MPM, you have whatever, meshless or FDM. So it has to be rely on this kind of weak form to have a more accurate or converge results. So we're gonna have some doubts in mind. Why can we apply such a small disturbance? Why we can do that? I will quickly go through a small part. For example, we have an integral function, which is the function we want to solve. Why this two, when I apply a small arbitrary function, why these two are equivalent? Because if your disturbance is arbitrary, I can put the sign to be always same sign as your original function. So in this sense, the integral, in order it to be zero, in order to guarantee the integral to be zero, your original function has to be zero, because my disturbance sign is always negative or positive sign. They have the same sign. So basically, these two are equivalent. That means a small disturbance looks like it's like a bad thing, but eventually bring a good thing. Basically, you are produce something from nothing. This is a high dimensional wisdom. So basically, it's not created by AI. AI can produce something from something, but this kind of high dimensional wisdom is produce something from nothing. So basically, I know that I truly understand this sentence. People mention about the nothing is important, thus I do nothing. I really understand why people are talking about this. So basically, it has a very physical and philosophical meaning. So basically, as a human being, we should try to produce something from nothing. Of course, AI can help us, but we have to generate new idea based on our human mind. Well, with the weak form, basically you can develop your discretize into domain and rely on FEM to solve your equation. That's just the subrouting steps. Of course, you can use other numerical methods as well. Eventually, you solve the problem within an element. Then you come up with your solution. Well, eventually you will end up with a system ordinary equations. Taking this unsaturated porous media as an example, you end up with you can apply multiple disturbance. For displacement, you apply disturbance. For pore pressure, you apply disturbance. For temperature, you apply disturbance. Eventually, you end up with a system of ordinary equations. So basically, you solve this large matrix, you end up with the solution. And of course, you need a strong solver for large sparse matrix, and you need some stabilization method when you have convection flow terms in your fully coupled problem. Of course, you cannot do that by hand. You can use MATLAB code to solve their problem first to really understand the process. But eventually, in order to solve the large-scale problem, I introduce a Moose and open system here. Of course, you can also rely on other numerical methods, basically open source code, try to solve this kind of problem. If you are from the industry, of course, you can also rely on something commercial, which what I introduced is some mechanicals from typically in mechanical domain of mechanical engineering, or the COMSOL one, which is for coupling. Of course, you can write you have to rely on your source code first, then move into their platform. Well, with this ideas in mind, I want to use my past career experience to show some application. Before joining Concordia, actually, I was heavily involved in petroleum geomechanics when I was in Calgary. But after I joined Concordia, there's no petroleum company in Montreal. I have to make a shift from petroleum industry to something else. I was still interested in looking to a temperature related issue. So that's why I'm picking up a geothermal energy and also frozen soil as a topic. But I'm still holding the trunk of the tree. That's why I can make the change smoothly. Basically, the thing is that the transition, it has to be we have to find the basics, the mechanics or the physics. I want to use the couple of example in petroleum industry. Firstly, the first example I want to introduce is the oil sands production process. We know that Total has a big disaster year in 2005, and there's a big leakage here about the caprock leakage because of the steam injection. So basically, from then on, but the government is pushing very hard on maintain their caprock integrity. So that's why we have to try to do the simulation to make sure your production rate is high, but you have to maintain the caprock integrity. Then we have to proactively use geomechanics to reduce injection pressure and try to produce the permeability to enhance the production. So the idea I want to introduce here is the one I work with my research associate, and so to propose a dilation and to enhance the production in the meanwhile, reduce the chance of the hydraulic fracturing. If we look at your rock fracture, the dilation basically come from there. When you shift, you have some dilation and you create some opening, increase the perm. For oil sands, when you have some rearrangement, you can also create some opening and increase the porosity, and that porosity is permanent because there's plastic deformation, and can also create some or increase some perm. So basically, if you look at the stress strain curve during shearing, there's some point you have at some point not the peak. You haven't touched the peak yet. Actually, you can have the transition from compaction to dilation. And from that dilation, basically it's kind of if in situ condition, your in situ stress is anisotropic. When you increase a little bit about the pore pressure, your effective stress path is trying to touch the yielding envelope, and gradually you touch the shear dilation yielding curve, then your porosity going to be increased a lot, then the perm may increase a lot. But instead, like traditional petroleum industry, they just increase high pore pressure in a short period, very high pressure. It will create some tensile fracturing behavior. So basically, that's kind of it's not the first choice. We can control injection pressure to create some dilation around your borehole. That will increase the perm, meanwhile reduce the chance of having the caprock failure. And here, of course, you have to do some laboratory test on the object and really know the plastic deformation behavior, stress strain behavior. Then you design to create some dilation room around your production and their injection wellbore. And it can be horizontal, can be vertical. So with that, then we can come up with the design to show that the well can the influence domain around the borehole, the porosity increase a lot. So basically, you can place some vertical well, you place some horizontal well. Of course, you have to inject some hot water, try to increase the porosity around the borehole. Then with that, we can carry out the numerical modeling about the reservoir simulation. Of course, it should be a coupled the simulation among the Abacus and the CMG. So because Abacus is dealing with thermohydromechanical coupled, but their fluid part is saturated case. But CMG can deal with the reservoir simulation. Then it's an iterative coupled. So with that, this example is showing that with this kind of dilation setup, your temperature is greatly enhanced. Basically, when temperature is more enhanced, your influence domain has been highly expanded, then your production rate gonna be increased a lot. That's one of the example. Then I think everybody noticed last year, the Journal of Petroleum Energy and Petroleum Science and Engineering changed the name to be Geoenergy Science and Engineering, and to leverage the path for geothermal hydrogen renewable energy. So basically, why the journal can make a change so smoothly is because the journal usually publish their papers which has a similar physics and still within the scope of geoenergy engineering. So basically, they have the similar governing equations. In line with that one, we actually I changed my my gears accordingly. Basically, in Quebec, so how can I? In Quebec, we also have some similar problem like petroleum. So for deep geothermal energy, when we try to produce geothermal energy, we want to guarantee the stability of the fault, the wellbore stability as well. So when you try to drill, of course, your cooling effect should be considered, because when you drill, originally the reservoir is hot. When you have a drilling fluid touching the original reservoir, there's some cooling effect. If such kind of cooling effect is considered, I can demonstrate that we carry out the coupled simulation. We can see that the sleep tendency is higher if it is non-isothermal, or if the non-isothermal aspect is considered, and also the plasticity. In this case, we simulate the sleep tendency and also the plasticity to be built around the borehole. We are also carrying out some numerical modeling on the fault activation process during injection and production. Of course, it's going to be a large-scale simulation. We use MOOS to carry out the simulation. The other aspect in cold region is that in cold regions, we have to touch frozen soil. Frozen soil is something it is even more difficult to study when I compare with my previous research on oil sands or soft mud rock. This frozen one is very sensitive to temperature, the phase change from ice to water. It's very sensitive, so we have to do some special design to characterize the stress spring behavior. So why this is important? How can it be applied? In cold regions, we know that under climate change, the permafrost is melting, for sure. And now, even now in Montreal, it's like more than 10 degrees like before. It's getting warmer, not to mention the northern subarctic area. So in order to maintain the permafrost, one of the possible choice is to place the ground source heat pump under the ground. And in the meanwhile, you produce geoenergy, but you are trying to extract heat from the permafrost. And then the permafrost got reduced in the reduction in the temperature, and the permafrost can be maintained. And we carry out, we use our source code to simulate a case in the subarctic area. We can prove that if you install this one for 1 year period, basically the permafrost can be well maintained. The subsidence, the sediment, can be minimized. So basically, if we can do this for regional scale for a community, we produce, and for a long term, the permafrost can be maintained. Your structure, your infrastructure can be well protected. The other things that we can also in cold regions, in summer there's whole day sunshine, but in the winter term, the whole day there's no sunshine. Well, basically, we can store the solar energy as hot water to be the ground, and during winter we can pump out hot water and try to make use of them. One of the key things that you store the heat into the ground. For a lot of over consolidated formation, like in the northern Quebec, northern Canada, they are over consolidated. Maybe you don't want to, you're not worried about the consolidation, but if the bound water is involved, basically when my recent paper showing that the bound water inside the clay, basically that can contribute to some pore pressure increase during dehydration process. We write their numerical FEM code to simulate the process. Basically, we can find the pore pressure can be well built up because of the dehydration process. So I don't want to go into a very detailed mathematical and a physical process, but you can go to our recent paper to look at how the equations was developed, how the simulation was conducted. and the wake form is also disclosed. So basically, if you are interested, you can look into the details. Another thing is in cold regions. Well, not all the permafrost or frozen media they are saturated. For example, you have I think in the media we have learned that the permafrost during melting, greenhouse gas will be released, and those things will contribute more global warming. So basically, they are not saturated. Under unsaturated soil, when we want to simulate the carbon process, it's more complicated because you have ice pressure, you have capillary pressure from air, water, surface tension. You have your fluid pressure. So basically, the pool pressure become more complicated. They are phase change from ice to water. They are phase change from water to vapor, and they are dry air. They are vapor. So basically, the coupling process is more complicated. So far, there's no enough commercial software which can handle all of this. So basically, we develop our own numerical codes based on the similar idea. We can try to figure out how the deformation is involved. And if you want to produce geothermal energy or carry out the geoenergy projects in this subarctic area or in cold regions or in permafrost, you can carry out a simulation to study the ground response from this aspect. So this is the recent paper. Also, you can look into the details. Well, with all of this, I want to draw a summary. Basically, pore mechanics can be treated as a topic which percolates into all aspects of geoenergy engineering now. And well, the thermal pore mechanics end up with a series of coupled nonlinear PD systems. We should grasp the trunk and understand its high dimensional wisdom. Basically, as a human being, we should try to produce something from nothing. It is consistent with the Eastern philosophy, like Taoism or the Buddhism. You want to produce something from nothing. Basically, this is something you want to compete with the AI technology. You produce some new idea from nothing. That's what human being can do. Well, so if we proactively make use of the thermal pore mechanics, it can enhance the transition to a sustainable geoenergy and geoengineering. Well, you can make use of the AI technology to help you, but your idea, you should firmly hook to the original source of the physics and the origin of the mathematics. Try to make use of the tool in a better way or in a sustainable way. With this, I would like to acknowledge all my colleagues and my supervisor, and also my all the group members in my energy and environmental geomechanics. And I really enjoy working with all of them, my past research associate, PhD student, master students, and also the support by INSERC and West-Grid Compute Canada. They provide a strong tool for carry out the simulation. And I also thank you very much for the audience for taking the time to attend my talk. And I will be very glad to answer any question if you have. Thank you.
Thank you, Biao. It is a very inspiring talk. So let's see if we have questions from the audience. If you have any questions, just feel free to turn your mic, or you can also turn on your camera if you want. Or you can also put your questions in the chat if you are more comfortable with that. So I guess I can start with my question
Right.
while we're waiting. So it's actually a very general question. I see you're mostly using FEM for those coupled process. So
Right.
with your experience, how do you compare this approach with other approaches like finite element or finite volume approach using explicit solving method?
Oh, yes, this is a very good point. Basically, the FEM one, it's when we deal with the small deformation, the advantage is very is considerable. It's for small string, but when you have deal with the post peak and dealing with the discontinuity, it has some limitation. It needs more effort to deal with the converge issue when you have their post peak failure process. But I think that was a trend now is combine FEM with DM or combine FEM with FDM. But the essence, I think, the DM eventually they want to combine with FEM to deal with large scale problem. So basically, they have all of them have its own advantage and disadvantage, and it looks like there's a trend to merge those different methods, especially when we have coupled problem. When we have a solid problem, most people rely on FEM. When we have fluid problem, mostly rely on finite volume or finite difference, because uh, based on Eulerian derivations is easier to handle. But eventually there should be a way to combine their advantage of both. Yeah.
Yeah, so do you have a plan to use other approach or like try other software?
Yes, so I think so far is basically for the problem which I have, looks like all the problem can be solved so far. But for the next step, when I deal with the post failure, maybe I have to go with the MP, material point method and FDM to see what's going on. But that's a future plan. Yeah. Yeah.
Sounds great.
Mhm.
So do we have any questions from the audience?
Yes.
Hello, Professor Lee. Hi.
Hello. Yeah.
Oh, very nice talk. Thank you very much for the talk. Yeah, I'm wondering because you show four PDEs, and then you show your solver, which is Abacus, and another solver I didn't remember the name. Is the Abacus solver used to solve like the energy equation and the stress equation, and the other solver used to solve the mass conservation equations?
You mean the solver? Okay, so I think you are talking about the coupled of Abacus and CMG one, right?
Is that the THM company solver you're using?
Basically, the Abacus one can deal with the coupled as well, but it cannot properly handle the unsaturated soil. I mean, multi-phase flow, Abacus cannot well deal with the multi-phase problem, multi-phase flow problem. For TH, thermal hydromechanical coupled problem, Abacus can handle. But for when you have a multi-phase flow, Abacus cannot handle. That's why if you have a reservoir problem, usually it's a good idea to use coupling between Abacus and the CMG. And someone also use flank with CMG coupling. Basically, it's iterative. It's not a fully coupling. Within a time step, you are assuming something is not changing. Within a given time step, you update the pore pressure and mechanical or property, then step by step to solve the problem. But if you write your own source code, if you have end up with a system of equation like this, basically you can deal with the fully coupling. You are solving one matrix, and all the variable, all the other thing you can solve with one solution. Then this is the fully coupled process.
Yeah, I mean the even though we use like the iteration between the Abacus solver and the CMG solver, as long as the iteration converges, the solution is still the same. I mean, with the fully coupled one. So the problem really lies in whether the iteration between the Abacus solver and the CMG solver converges or not, right?
Yes. Yeah.
Yeah. But here's the problem. I also working in the THM coupling field. I'll encounter such a problem. I don't know, because the coupling between fluid and the stress is due to like the volumetric strain rate, right? It's
Yeah,
divergence. Yeah.
because the mass balance is contributing to the volumetric change.
Yeah, this is a very strong coupling effect, I would say.
Yeah.
So for this, the fully coupled method you mentioned here, because we need to introduce the Newton-Raphson iteration to solve the nonlinearity.
Right.
And but for the iterative between the Abaqus solver and the CMG solver, so this iteration doesn't seem to converge according to my experience, because the coupling between the fluid pressure and the stress is so strong, they just can't be separated.
Yeah, it's kind of that's why that's an iterative coupling, because you make the assumption within the given time step, when the variable is not changing. So that's why the accuracy is not as accurate as the fully coupling one. So you have to use a very small time step. That's why the computing speed, you have to rely on a large computer to carry out the simulation. And you have to use a small time step in case of bringing too much residual. Yeah.
Okay.
Yeah.
Yeah, cool. Yeah. Thank you.
Okay. Thank you.
Let's see, we have a question in the chat. So that's from Far. Do you want to turn on your mic, or you can maybe read it and to the audience?
Okay. So Farah is mentioning that all the geomechanical issues you mentioned are related to conventional geothermal energy extraction. What are your views on the issues due to geothermal energy extraction from low, moderate geothermal energy resources? So this is you mentioned about the extraction from low, moderate. That means from low enthalpy. That means shallow geothermal energy, or some energy, the temperature is not that high. Do you mean that? Or yeah, if so, it's kind of as what I mentioned there. It's the process is kind of similar, because you have handled the high temperature one, the lower temperature one is easier to handle, because your temperature is lower compared with your, because shallow one, the pressure, the confining pressure, and also temperature is lower than your, looks like you have your stronger tool, you solve a smaller problem, then it's just changing the material property and the boundary condition. So it can be applied to their waste their abandoned mining. And now it's a hot topic to make use of geothermal energy from abandoned their gas wells or abandoned their mining sites. So those area, it's, I think the physics and the mathematics are just the same. Yeah. Hopefully that answer your question.
So, if I may.
Yes,
okay,
please.
Kian?
So I have a question. So I was wondering, you mentioned cold region soils. So I was wondering, what kind of soils are we dealing with? And is it true that we have unfrozen water up to very low temperatures, even though we are below the freezing point of the water in those regions?
Oh yeah, in coregions depends on where's your latitude. You know, in some areas, subarctic area, the temperature can be -50, especially in the active layer. So the temperature can be up to a -50, and of course it's getting warmer now. But we still have when people are dealing with Arctic engineering, drilling, or exploration in Alaska or northern Canada. So we do have some very low temperature soils, or not only permafrost. We have the active layers, which can, even though during summer it's just the soil, but during winter it can be -20, -30. It's possible.
And they could still contain water, right? And not just ice.
It contains, yes, because it depends on the mineralogy. For example, when we have clay involved, because of the diffusion double layer or the bound water effect, the fluid water is still there. even though it is -40, -50, clay soil is still like it's not that brittle. You still have some movable water there. So those kind of water people use NMR, nuclear magnetic resonance method, usually used in petroleum industry to quantify bound water. And this kind of water can be quantified using this NMR technology. Yeah.
Thank you.
Okay, thank you. I think we have another question from our Alexandra. Thanks for the presentation. How do you think DM-based modeling is response to FEM-based, also in which TM coupling is more easy to establish? Well, yeah. Now DM is also very popular in dealing with coupling. Yeah. So yeah. So if that's the question, then to me, I think FEM is easier because to me, for example, you just change the for example, you end up with the governing equation, you change to be weak form. Let's say you change to be weak form. When you have coupled, you just solve the equation. So then the rest is just the subroutine. But for DM, I didn't deal with DM before. Recently I just got in touch with the DM modeling. But of course, it is also solving the coupled equation. But to my understanding, so the constitutive model for failure criteria is easier. That's why a lot of people are pushing hard to work on the DM modeling their failure process. But for the temperature, for the multi-physics, FEM, because it's a more physics and mathematics based. So to me, it's easier to handle when we deal with coupling for the numerical methods. Okay. Thank you.
And I guess if you are pursuing grain scale behavior,
Yes.
then
Yeah.
probably you would have to go with DM as well. Yeah.
Exactly. Because the FEM is mostly for the failure criterion is phenomenon based. It's homogenized actually. When you really want to touch how, for example, how the soil particle is cracking and how they're crashing, that has to be handled by DM. But eventually it can be combined. For example, you use DM to study the micro scale behavior, but you sum up with the phenomenon-based failure criteria and implement in the FEM to simulate large scale problem. So basically, for example, in our field, of course, you cannot see any grain. It's a large scale, so FEM is stronger in dealing with large scale problems than it's gonna be somebody use FEM cubic. So basically, FEM deal with the grain scale, FEM with the lab scale, and FEM in the field scale. It's a similar idea, but to my understanding, it's better to replace the first skill with DM. Then the second skill and the third skill will still use FEM. Yes. Yeah, Professor
Well, I have
Shin.
a,
Hi,
yeah,
Professor
so
Shin.
nice.
Very nice seeing you here.
Yeah,
Yeah.
nice.
Go
Thank you
ahead.
very much for such a wonderful talk.
Thank you.
What I've been thinking is that suppose if I have to plan experiments to validate your FEM results, and this is where the question would be that to what temperature range I would be exposing the material, and what changes at porous scale the material would be experiencing because of these temperature changes. This is not a question, maybe a sort of a realization,
Yeah.
which is very, very important to realize. So do you have any ideas to throw some light on this?
Yeah, exactly. There, as what I showing in the couple question, my simulation go is from frozen one to the high temperature one. So it depends on which engineering geoenergy problem is we are solving. So if for gas hydrate, it's gonna be a low temperature. It's gonna be frozen one. And for deep geothermal one, it's gonna be well, geothermal, even the deep geothermal, we have the EGS and also other types. It also has different temperature range. Basically, it's kind of for lab scale. What's easier is that if your temperature is below and the phase change is below the phase change point, it's easier to validate. When there's a phase change behavior, for example, from gas to vapor or from gas hydrogen melting, when there's a phase change one, the validation become quite complicated. The point is, our experience is that the boundary is difficult to control. For example, how much gas pressure it is, which kind of air pressure along the boundary it is, it's very difficult to control. So for validation, we'd better maintain the phase change to be some range. Yeah.
Okay, thank you. Let's try to do some experiments and validate your
Yes.
FEM models. That would be very
Great.
challenging work, but very nice talk. Great. Thank you very much.
Thank you. Thank you.
Okay, I think if there are no more questions from the audience, let's thank Biao again for the wonderful, wonderful talk, very inspiring. And I hope like when you have some new results, you can come back and give us another talk.
Okay. Sure. Thank you very much, Wei, and greatly appreciate it for the invitation. And thank you everybody for attending this talk. And I will be very glad to discuss more. If you have any question, you can send me email or through any channel.
That's great. Thank you, everyone.
Thank
I will
you.
see you in 2 weeks.
Thank you. Bye-bye.
Bye.